Hello everyone, and welcome to this new and exciting session in which we are going to discuss the ResNet model. This model was first introduced in this paper entitled Deep Residual Learning for Image Recognition by Kamin et al. And up to date, that's about 7 years later, this model is still greatly used. And the high performances gotten when working with the ResNet model come due to the fact that the ResNet model relies on this residual block right here, which permits us get even better error rates, as we could see here, as compared to the VGG and Convolutional models. In this section, we are going to focus on understanding how this residual block works and how the ResNet model is constructed based off this model. Don't forget to subscribe and hit that notification button so you never miss amazing content like this. These curves right here depict the limit of models like the VGG, which are just based on stacking up conv layers. To best understand this plot, recall that with the ResNet we had fewer number of layers. So we started out with ResNet, fewer number of layers, and then we moved on to VGG, where we had the VGG 16 version, then the VGG 19 version, and then we expect that if we keep increasing this number of layers, then the error rates should be dropping. But what happens actually is the opposite. So what goes on here is, you see, for this 20 layer network, we have a lower error rate as compared to this 56 layer network. So we expect that this instead should be lower than this because this we've stacked more conv layers, but that's instead the opposite. Now this same phenomenon is witnessed with the test set. So here there's a test and here's a training. So for the test 2, we have the 20 layer performing better than the 56 layer. And so it's clear that just blindly stacking up conv layers wouldn't help in making this or in dropping the training and test errors, even though they are more expensive. And this is why the ResNet model introduces this residual learning, which is based off the residual block, which we've seen already. Here's the residual block. Now note that this weight layer here, or those weight layers here, are simply convolutional layers. And so now, unlike before where we will just stack this here, let's call this WL for weight layer, stack this weight layer, and then we'll stack this other one, and then we'll keep stacking up that way. Just keep stacking up like this. Now what we'll do is we create a connection between the input and the output. So we create this connection, and then here there's some addition. So we get this output and we add it with this other output right here to produce now this new output. So here if we suppose that this input is X, and then what goes on in here is f of X. So let's change this to red. What goes on in here is f of X. That's this f of X. Here we have this f of X. Then our output can be given as h of X, which is simply equal f of X plus X. That's the input plus its output. Now to produce this new output, h of X. But again, to better understand why we need this residual block right here, we need to first understand why models which are based on just stacking up the conv layers like the VGG actually underfit even when you add up or when you increase the number of layers. Now the reason for that is exploding and varnishing gradients. So let's explain what it means for gradients to be vanishing. Now recall that in the gradient descent process, we have a weight, and this weight, the way this weight is updated is such that we take its previous value. So we have the previous value of the weight minus the learning rate here. Let's call it LR, generally denoted alpha, minus this learning rate times the partial derivative of the loss with respect to that given weight. Now during the training process, in order to compute this partial derivative right here very efficiently, the method used is backpropagation, or one of the most common methods used is that of backpropagation. Now the way backpropagation works is that you have, say, this model, let's call this model M, and then you have some input right here with the output. Obviously you have what the model outputs, and let's call the model output Y cap, and then Y, that's not from the model, we have Y right here, which is what the model is expected to output. Now it's this difference that produces the loss, and we're finding that partial derivative of this difference with respect to each and every weight which makes up this model. Then if we split this up into different layers, let's just say we have different layers like this. Note that each layer is composed of several weights, but let's say we just split this up like this. Now the layers, this layer has its own weights, but one point to note is that during the backpropagation process, to obtain the partial derivative of the loss with respect to this weight here, we make use of the partial derivative of the loss with respect to weights which come after the layer, or which come after this layer right here. So to get this here, we will need this different partial derivatives. To get let's get back to get this, for example, to get the partial derivative with respect to this weights here, we will need this others right here. Now the problem is, if we have this here, and also before going to explain the problem with this, is that we need to understand that to get, for example, let's take this one, to get, for example, the partial derivative of the loss with respect to this different weights, there are many weights in this layer, let's say weight for this layer is actually equal some values, let's say alpha 1 times whatever value times this partial derivative of the loss with respect to this weights here. So let's consider that this is the seed layer 1 2 3 4 5 6, then L6 here, we have L7, layer 7. So because we're multiplying here, it means that if while getting this partial derivative we obtain a value very close to 0, if we get a value very close to 0, say 0.000001 for example, it means that it's going to affect this other partial derivative in the sense that this too will be a very small value. And if these partial derivatives are too small, then we will not get a change in this weight, because you have the new weight you're trying to get being equal to the previous weight minus a very small value here, and so there will be little or no changes in the weights. And that is why, even though you keep increasing this number of layers, let's take this off, even though we keep increasing this number of layers, we cannot achieve better performances due to this vanishing gradient problem, as the model is now finding it difficult to update its weights such that the training error can be decreased, since the gradients right here are vanishing, that is, they are getting towards 0. So now we've just seen that making our network deeper or increasing the number of layers makes it difficult to propagate information from one far end to the other end. And so what the authors suppose is that if the added layers can be constructed as identity mappings, a deeper model should have training error no greater than its shallower counterpart. So this means that you have this model, let's suppose this model, and then this is the shallower model, and then this is the deeper model right here. And we're saying that if we construct this deeper model such that it's identical to the shallower model, so basically it's the same as this here, with changes in blue. So we have this same shallower model, and then the remaining layers here, these other layers here, are constructed such that this is the identity function, or a group of identity functions which are stacked together. Then the training error of this one, although deeper, shouldn't be greater than this training error right here, or the training error of this shallower model. And so this means that if we want to pass information from this point to this point right here, and that this weights or the values in here dampen this information, then there is this path right here which permits us simply copy this input information to the output. And obviously this is simply the identity function. And so here, if after passing through say 20 layers and we get to this point, so let's consider each and every one of this is a single layer. So we've gone through 20 layers, and then we've gotten to this point where the values we get in here are almost zero, such that when this information passes, it's going to be also or practically zero. Then there is this path which at least restores this exact same input we have here. And so this means that just as the authors of the papers supposed in this example we took here, if we make our model or our neural network deeper by adding this residual blocks, then there will be no increase in the error rate. And in practice, this instead leads to a decrease in the error rate, which is exactly what we want. And one other argument which accounts for the fact that this residual blocks help in improving the performance of the model is the fact that since we have several paths, this residual model now looks like a combination of several shallow models. So it looks like you're combining different, let's draw it better, let's get back. It looks like we're combining this shallow model here with this other shallow model with this other shallow model, and then producing what we call an ensemble of models, or an ensemble of shallow models to be more precise, which help in making the overall model much more performant as compared to when we just have a single path. So another way you could look at this is that for this, let's take this first shallow model. You could have information which passes this way and then gets here and then goes this way. So that's the first model. And then another time you could have information which goes this way, goes this way, goes this way, and you have this other model. You could have another situation where the model goes this way, it goes this way, and then goes just straight and giving us this other model. Later in this paper entitled Visualizing the Loss Landscape of Neural Nets, Lee et al. Produced this visualization here which shows a ResNet without skip connections and a ResNet with skip connections, and this shows how easy it is, or how easier it is for the weights to find their way or to get the optimal weights which minimize the loss as compared to when there are no skip connections here. It should also be noted that this addition we have here is an element-wise addition. And so we have to ensure that the dimensions of this input should match the dimensions of the output we have here for this operation to be valid. Now in the cases where, these two aren't equal, then we need to do some modifications in this skip connection right here. Now when we look at this three models compared, we have this VGG19, we have this 34 layer plane convolutional network, then we have this 34 layer residual network. We find that we have this skip connections, that's our residual block. So this is our residual block right here. We stack this residual blocks now instead of just stacking the conv layers as we did with the VGGs. Now we stack the residual blocks, and then sometimes you could see here, sometimes this line is solid, sometimes it is dotted. Now when it's dotted like this, it's simply because there's gonna be a change in the dimension. So if you notice here, you find that every time we have these dotted lines, you find that there's a change here in the number of channels. So here you have 64 channels, and then here you have 128. And so since we get in this 64 channel input and we want to match this with 128 output we get in here, then we need to do some adjustments here. Now, as we've seen here, or as we can see in the paper here, there are actually two ways of making these adjustments. The first way is this A, the next one is this B. For the A, the shortcut still perform identity mapping with extra 0 entries padded for increasing the dimensions. So to get from 64 to 128, we add this extra 0 entries. Then either we do that or we take the B, that's the projection shortcut, which was presented in equation 2, is used to match the dimensions. But this is actually done using one-by-one convolutions. Now, to better understand how the one-by-one convolutions work, let's take this example where we have this input size 10 by 10, kernel size. Now, since it's 1 by 1, then the kernel size is 1. So this is, we have just this one weight right here, and then you see it just goes through each and every pixel value. So here we have this, and then notice that the input is the same shape as the output. And so if, for example, you have this input made of 2 channels, let's add a second channel. Let's suppose this input has 2 channels. So we have this one channel and this other channel right here. Then to obtain an output of, say, 4 channels, so we have this input, 2 channels, so it's 10 by 10 by 2 channels. And if we want to have this output to get to 4 channels, all we need to do now is just make use of the one-by-one convolution, and then we add the we have 4 of these different weights, or there's four of these different kernels. Since it's obviously 1 by 1, if we were 3 by 3, then we would have something like this. We would have 4 of this. Now it's 1 by 1, we have, you see here, 4 of this, and then in that case this one will give this output, then this other one will give this other channel here, this other one, let's change the color, this other one will give another channel, which we'll just add here, then this other one here, let's take that to be green, will produce this other channel. So that's how we can move from these 2 channels to 4 channels. And so in the case of the ResNets, where we want the inputs, we get some inputs, let's say 64 channel input, and we want that at the end, we want that this input, what we have here, should match with this output, which is already 128. 128 here. Then we need, we could add this one-by-one convolutions with a certain number of filters, such that we could get this desired number of channels here. So here now we could have 128 one-by-one filters, and then this now will match up with this output right here, such that we could carry out the element-wise addition. And now the difference with the VGG and other previous conv nets is that instead of making use of the max pool, as you will have here, you see this pooling layer with pool size 2, what we do here is we use our 3 by 3 convolutional layer, but we use strides. So we specify the stride number of 2, and this permits us to downsample this feature maps right here. Again, we could check this out here. Let's suppose we have this 3, and if we're to do or if we want to downsample this, what we could do is increase the number of strides. Let's take that to 2, and you see this is going to be downsampled. And if we take the padding to 1, you find that the output is half of what we have here. Then the authors also make use of augmentation and then batch normalization, where they apply this batch normalization layer right after each convolution and before the ReLU activation. Now, batch normalization is this technique for accelerating deep neural network training by reducing internal covariate shift. To better understand batch normalization, we'll start by explaining the notion of covariate shift. To better understand the notion of covariate shift, let's suppose that we're trying to build a model which classifies or which says whether an input image like this one or say this one is that of a car. So it's either a car or it is not a car. Now, if you're building this kind of system and then you start by or you create batches of these kinds of toy cars and you pass through the model, and the model learns how to see this and know that it's a car, and sees some other image and knows that that's not a car. Then later on, when you take a car from this other distribution and you pass into our system, it becomes difficult for the weights of this model to adapt to this change in distribution, though the inputs are all cars. And to visualize this, let's consider this plot right here. What we're gonna have is something like this. So we'll have this here for car, and then this for not car, and then we'll build this classifier or this model which distinguishes a car and an image which is not a car by, say, this function, for example. Now, when you bring some other distribution, like say this distribution, you would have something like this. You see, you have something like this here, this other distribution, and not car. Let's say not car is about this, and then you would need to have something like this to separate the cars from images which are not cars. And this then makes it difficult for us to have a function which separates images which are cars from those which are not cars when those images come from these two different distributions. Now, this shift here is known as the covariate shift. And so that's why most times before passing the image into the model, what we do is we normalize this input. So let's suppose we have an input X. We generally carry out some normalization in order to account for this covariate shift. So now after normalization, what we're gonna have is that all these images, be it from this distribution or this other distribution right here, will now have been normalized to reduce the effect of the shift. And so now we could have our single, or could have this function which separates the cars from the non-cars, and with much more ease. Now that said, what if this kind of covariate shift instead happens in the hidden layers? That's these layers which make up the model right here. So let's suppose that we have some conv nets like this stacked with the activation functions, and then we have this weights, that's this parameters which make up which are part of the layer, now coming from different distributions. Then in this case we have an internal covariate shift. And to remedy this situation, we now make use of the batch normalization. And the algorithm for the batch normalization is described in the paper. So here we have a mini batch and we obtain its mean. So here we try to obtain the average value of the different weights. Then we also obtain the standard deviation, which is sigma, and the variance, which is sigma square. So basically we obtain the mean and we obtain the variance, and it's this that we make use now to normalize our data. So now you take every weight, you subtract by the mean, that's here, which was calculated here, and then you divide by this standard deviation, and then we add this small epsilon to avoid having a very small number or 0 at the denominator. So that's it. This is how the normalization or the batch normalization process goes on. And it should be noted that there are other normalization techniques like the layer and group normalization, which are kind of similar to this but different, in a sense that with the batch normalization, this mean is calculated over a given mini batch. So like here, this is the mean of values calculated in the mini batch and the standard deviation from that mini batch. Now after getting this new value of x chapeau, what we now do is we multiply it by gamma and add beta. Now this gamma and beta are actually trainable parameters. So when working with batch normalization in, say, TensorFlow or PyTorch, you'll notice that the batch norm layer will also have its parameters. Now here, the role of this gamma and this beta is to scale and shift, and these parameters are learned along with the original model parameters and restore the representation power of the network. And so when we set gamma to be the square root of the variance and beta to be the expectance or the mean of x, then we could recover the original activations if that were the optimal thing to do. So essentially what they're saying here is, if it's instead optimal for us not to use the batch normalization, then we could adapt the value of gamma and beta such that we get this original value of x right here. And the way this can be done is quite simple. All we need to do here is multiply this x by, let's say, gamma square plus epsilon. So we have gamma square plus epsilon, and then once we've multiplied this, you see, once you take this here and multiply by this, you set this to like this, do this, this cancels out with this, and you're left with xi minus the mean. Now when you're left with xi minus the mean, if beta is equal to the mean, then you would have xi minus the mean plus beta, which in this case is the mean, and you see it cancels out and gives you xi, which is this original value of x. So if we set our beta to be this, or rather our gamma to be this, and our beta to be the mean, then in that case we retrieve our original value of x. And so that's why you see these two parameters are trainable such that we get the best values or the most optimal values for gamma and beta. Then there's also this initialization, that's the model or the network is trained from scratch. Stochastic gradient descent is used with a mini batch size of 256. Learning rate starts from 0.1 and is divided by 10 when the error plateaus. So basically, when we get to the point where, let's have this, when we get to a point where the error starts to plateau, then at that point we could update the learning rate from 0.1 to 0.01, and then if it plateaus, if it drops, you see, and it plateaus, let's go this way, it drops and plateaus again, then we carry out this same computation. Now that said, is for over 60 times 10 to the 4 iterations, where decay and momentum are used, and there is no use of dropout. So again, in testing here we have different scales which are used and average. So we pass the image at these different scales, and then the average value or the average scores are recorded. Now before we move forward to check out some results, it's important to note here that after this last conv layer, we do not carry out flattening. Instead, what is done here is average pooling. In order to better understand how the global average pooling works, let's consider this example from peltarion.com. So right here, we're supposing that we have this as the output of the final conv layer. Then what we do is, instead of just flattening, that's just picking all those values and flattening them out and then passing through a fully connected layer, what we are going to do is, depending on the number of neurons we want the next fully connected layer, we are going to create a certain number of channels. So here, for example, we have this depth here. The number of channels here is 3. We have the height and we have the width. And then, since we're actually doing global average pooling, then for each and every one of these channels, for this channel, this channel, and this channel, we're gonna get the average value. So here the average value is this 8. Here the average value is this 3. Here the average value is this 5. And so if you want 1,000 of this, then you should have a depth of 1,000 right here. And now with this, you see that it looks quite similar to the flattened layer, as now you have all these different values, or these different single values, which can now be passed into a fully connected layer. Now it should be noted that in certain tasks, like in classification, which we are trying to do, this global average pooling will be great, as the position of the pixels don't really matter. Now this simply means that here, since you get this average, and here you get this average, you get this average, it means that this position or this pixel wouldn't be close to this other pixel, as in the case of the flattening. But since, like in our case, we're interested in saying whether a person is angry, happy, or sad, the positions of these output values right here won't really matter as much as it would have mattered in the case where we're dealing with an object detection, or say object counting problem, where the particular position of the person or of whatever we are trying to detect actually counts. So to better explain this again, let's consider these two examples, example 1 and example 2. Right here, for classification problems, all we're interested in is in detecting that this person is happy. So whether we have a face this way or this way, the position doesn't really matter. All we're interested in is in knowing whether this person is happy, angry, or sad. Now, for object detection, the exact position of the person matters, and so the exact position of this neurons here will matter. And so employing global average pooling for such tasks isn't a great idea. So in summary, if you have a task where the position doesn't matter that much, then you could use the global average pooling. If not, then you're advised to use the flattened layer. From here, you could see the different variants of the ResNet. You see here we have the 18 layer ResNet as a ResNet 18, ResNet 34, ResNet 50, ResNet 101, ResNet 152. And here we could see that with the plain networks, that's without the residual block, you find this 18 layer performing better than the 34 layer. But once we have the ResNet block, you find the 34 layer performing now better than the 18 layer, meaning that we could now go deeper. We also have this table right here, which shows the VGG model, the Google Net, the PRLU UNet, and then the different plane networks and the residual networks. It shows clearly here that the ResNet 150 performs best, regardless of the fact that it is deeper than the 101 and 50 counterparts. And before we move on, also note that here this ResNet block, as you can see here, is composed of these two conv layers for the 34 layer, while from this 50 to 150 layers, the ResNet blocks are composed of 3 layers or 3 conv layers, as you could see right here.